Alright, ladies and gentlemen, welcome to the first video on equilibrium. In this video, we're going to talk about control of reactions, we're going to talk about rates and rate laws again, and we're going to convert those rate laws into how we actually define the equilibrium state. So to start off with, we'll talk a little bit about control. Now, we've already talked about thermodynamics and kinetics. Right, so thermodynamics is all about whether a reaction is energetically favorable. So is delta G less than 0? Now we can actually go about controlling a reaction and making things that are energetically unfavorable or non-spontaneous occur spontaneously. One of the ways that we would typically tend to do that is through a process called coupling. Right, so if we consider, for example, the reaction to produce ATP in your system, right? So we have adenosine diphosphate, ADP, which is the low energy form of the molecule, and we add phosphate to it. So phosphate in biology is usually abbreviated as Pi. This is just the phosphate ion PO43-. Right? So if we do this reaction, we will produce ATP, or adenosine triphosphate. The problem with this reaction is that for this reaction, delta G is slightly above 0, so it's not energetically favorable. What we wind up doing is we actually couple it to another reaction. Right? So if we take glucose, for example, so if we take glucose plus oxygen forms CO2 plus H2O. Right, so just our normal cellular respiration. This reaction, delta G for this reaction, is much, much less than 0. This is very energetically favorable, right? Very exothermic. If we couple these reactions according to Hess's law, if we add the reactions, we add the delta G's, the reaction overall becomes energetically favorable, and we can actually recharge, quote unquote, our ADP into ATP, which gets used when we need to convert things into energy later on in the process. Kinetics control, we already talked about a little bit. So kinetics is how quickly the reaction happens. Right? So the way that we can affect a reaction and get it to happen more quickly, a couple of different ways, right? We can increase the temperature. Right? So we can change temperature. Increasing the temperature generally causes the reaction to go faster, again, because we have more molecules that can overcome activation. We can similarly decrease the rate of reaction by lowering the temperature. Now, temperature also does play a little bit of a role in thermodynamics when we're talking about the role of entropy, right? So, for certain combinations of reactions, if we change the temperature, the entropy term can change by enough to overcome enthalpy and change the delta G from positive to negative or negative to positive as we choose. All right, so temperature kind of controls both. The other thing that controls kinetics, which is a little bit more substantial, is going to be adding a catalyst. Right? Catalysts lower that activation energy barrier by providing a different pathway, which means that since it's a lower barrier, more molecules can react. Reaction occurs much more quickly. Right? So we've already learned how to control reactions using thermodynamics and kinetics. Now we're going to learn about using equilibrium. So thermodynamics is energetically favorable, yes or no. Kinetics, fast or slow. Equilibrium, how far does it go? Does it go 100% of the way to completion? Does it only go part way? Does the reaction not really want to go anywhere at all? Right, so that's what we're going to be talking about in this unit, is how to figure that out for any reaction, and then some ways that we can manipulate reactions to make unfavorable reactions happen or cause favorable reactions to stay put. So just a little bit of a review of a reaction rate. Right, so what we know is that the rate of a reaction is proportional, among other things, to concentrations. Right, the higher the concentration, the faster the rate. So let's, for example, consider a reaction. The reaction I want to consider is the reaction between NO2 and N2O4. Right, this is actually a very simple reaction. All that's happening here is that the NO2 molecule, each NO2 has a single lone electron on the nitrogen. Those two lone electrons combine to form a bond, making N2O4. Right, so if we look at the forward reaction, what we know for the forward reaction is if we do reaction rate, so we'll talk about rate as a function of time. So this will be for NO2 going to N2O4. Right, so this is our forward reaction. Right, so as the reaction proceeds, the concentration goes down, which means the rate of reaction will slow down. Right, now, similarly, if we talk about the reverse reaction, we start with no product. Right, so the reverse reaction actually has a very low rate to begin with. So this is going to be N2O4 making NO2. So this is our reverse reaction, right? So rate versus time. We start with no product, so the reaction rate is going to gradually get faster and faster and faster as we go along, as we form more and more and more product. Right, so reverse reaction will speed up because the concentration is getting bigger. So equilibrium is about the interplay between the rates of this forward reaction and the reverse reaction. Right, so our overall definition of equilibrium, is when the forward and reverse reactions happen at the same rate. Right, so when our NO2 forward reaction is occurring at the same rate as our N2O4 reverse reaction, we've reached equilibrium. At that point, you won't see any changes in the reaction rates. And since you're not going to see any changes in reaction rates, you're not going to see any changes in concentration. Right, so the amounts of product and reactant, once you reach equilibrium, remain constant. Now, a couple of things to keep in mind about this. First off, equilibrium is dynamic. Just because the amounts stay constant doesn't mean the reaction stopped happening. The reaction is still proceeding in both directions simultaneously. It's just that as soon as you make a product, it's being turned back into reactants by a competing reaction. Right, so the reaction is always going on. And the second thing to keep in mind is that even though the rates of the reaction are the same, the concentrations are not. Right, so if you look at our N2O4 reaction right here, notice how at equilibrium we have a lot more NO2 in this mixture than we have N2O4. This depends on initial concentrations and rates and all that sort of thing, but we'll actually be able to work with this math once we get to it. Right, but please notice, even though the rates are the same, the concentrations don't have to be the same. They just level out at some point. Get used to looking at these graphs. There are going to be open response questions, especially for this graph down here, that will ask you to draw this graph for multiple substances in a reaction. Right, it's a very common open response question that they'll give you is to ask you to draw it, or they'll give you options of what the graph should look like as a multiple choice question. All right, so this is the introductory video on equilibrium. Again, we're just talking about how to get to the equilibrium state, which is achieved when reaction rates are the same in both directions.